Okay, so it's really great to see all of you here again with so many faces that I recognise now at this stage. And I really hope that you enjoyed Austin's lecture last week. I've heard already from some of you that you really did, and that's fantastic. So today we're going to be continuing with that idea of mapping the dark sector. So I started this with you 2 weeks ago where we spoke about dark energy, and I hope I convinced, spoke about dark matter, and I hope I convinced you that dark matter really does exist, and we have very strong evidence for it. So today I'm going to talk about what is dark energy, and why we think there is dark energy out there, and then I'll cover the kind of muddy waters of the fact we don't know what dark energy is, and in the next lecture next week we'll go into more detail about that. Okay, so this is a picture that you're used to seeing at this stage, this cartoon image of time from the very beginning, from the moment of the Big Bang until today. And this notion of an expanding universe. Okay, so things starting off very, very small, and then we have the release of the cosmic microwave background, this radiation in a very early period, the first stars igniting, turning on, and illuminating the universe then expanding, galaxies forming, our galaxy forming, us forming, and then us creating the WMAP satellite, which is able to record all of our history. And then today's lecture will be about this very late stage, which we think has just kicked in relatively recently in the history of the universe, which is this accelerated expansion. So, just to remind you again, this is the pie chart of the constituents of the universe as we think it exists. So, this is this dark matter, which I spoke about 2 weeks ago, which makes up about 23% of the constituents of the universe. And then dark energy, which makes up the majority. So this really big unknown component that is one of the biggest mysteries in cosmology today, it's fair to say. Because we really don't know as much about dark energy as we know about dark matter. And then the stuff we do know about makes up this tiny, tiny fraction of the pie chart. And that's all the stuff we're familiar with, the stars and the gas and you and me. So dark energy, we need to throughout this lecture, not confuse dark energy with dark matter. And I know a lot of you might be unhappy with the name dark energy and dark matter. And that's fair enough, but we're stuck with them, right? But they are very, very different things. Yeah?
We see this diagram many times, but what that means, 23% dark matter or 3.6%.
So I'm going to go on to that.
Is that represent amount of energy in the field?
So I'm going to talk about these fractions later on, and exactly, I'm going to show you the equations that what these fractions represent. Okay? Yeah. And if it's not clear at the end of the lecture, then you can ask your question again. Is that okay? So these are fractional, dimensionless numbers. Okay. So it's a fraction of the total, and I'll talk about what that total is. Okay.
Of what?
So it's the total energy density to stop the expansion. So in a couple of slides, we'll go into that, okay? You have to believe me. And if you're not happy at the end, then we can go over it. If you don't believe me, go.
No.
Okay.
Believe is not good.
Okay, so, hopefully by the end, this is my mission to convince you of this number. Okay, so dark energy is not made of massive particles. That's as far as we understand it. And we do understand it, it's an energy field. So what is a field? So the way we define it is, an energy field is, you can think about it like a temperature map, for example. Okay, so at every point in space and time, there's a number associated with the temperature on the surface of the Earth, for example. Okay, it's just a single number, 35 degrees Celsius or whatever in Fahrenheit, and that's a number that you associate in every space and time on the surface of the Earth. Okay, so that's what we mean by a field. And in a sense, this dark energy field is something that has a value at every point in space and time in the universe. Okay, so just to drive home this message of dark matter is not the same as dark energy, and I will go into why we believe that's true. And then our name for the standard model is this lambda CDM. So the CDM part we covered in quite a bit of detail 2 weeks ago. The CDM stands for cold dark matter. And we covered why we thought it was a cold component and why we thought it was a dark component, meaning it just doesn't interact with light. And then this lambda part, it's called lambda for historical reasons, but this is the part referring to the dark energy component. Okay, so really, if you want to keep in your mind that dark matter is this cushioned particle, then that's a good idea. But dark energy is very, very different. So I don't think, on Particle Zoo, I don't think there is a dark energy cushion, but maybe I'm wrong. Okay, so just to put this in context, we did talk in the very, very first lecture about how our current cosmological model came about. So why people came to the conclusion that we do have expanding universe, and this notion then of the Big Bang, if everything is expanding today, and you run the clock backwards, then you're left with this singularity at t is equal to 0, where everything started. So this is the idea of an expanding universe, and this came about in the early 1920s when Einstein wrote down his equations, and then many people argued, including Einstein and de Sitter, pictured here, about the interpretation of that equation, so solutions to that equation which could possibly represent our universe. And Einstein at the time, and a lot of people at the time, thought that the universe should be a static and unchanging place. This was a very attractive notion for them. And so Einstein really tried to make this work in his equations. But it turned out that based on observations made by Edwin Hubble in particular, that there was very, very strong evidence for an expanding universe. And it turns out that Einstein's equations did allow an expanding universe, but because of his preconceived idea of having a static universe, this is why people did not find it immediately. And it actually was Friedman that found the solution for an expanding universe. So I just couldn't resist writing down Einstein's equation because I think it's really beautiful, and this is what it is. So this is Einstein's equation. I haven't written out the terms here, and there's no need to go into the detail of it. But basically, you can break it down, and a lot of people think about it in terms of a left-hand side and a right-hand side. And the left-hand side, this g mu nu here, is really describing the structure of space-time. And the right-hand side is all the stuff in the universe, okay? All the matter and energy in the universe. And it's important that you consider all the energy as equivalent to being all the matter. Okay? We'll talk about that more in a couple of slides. And then these three factors here are just some constants that we don't really need to worry about. C is the speed of light, G is Newton's constant, and pi is just a fundamental constant. Okay, so in this equation, you can really see, without going into the full details, you can see that this is where this old notion, our familiar notion of general relativity, that space-time tells matter how to move, and matter tells space-time how to curve. Okay, and this equation is where that expression comes from, okay, because the two sides must equal in this equation. So general relativity really describes this fundamental connection between how the universe is expanding and how that is driven by all the energy in the universe. Okay, so it's this connection between the two. So if we want to talk about all the stuff in the universe, so at the moment I'll just talk about this right-hand side. I'm adding up all the components that are in the universe. And what we generally talk about is this omega here. So when I show you that pie chart, and I say 23% of the universe is made up of dark matter, and 74% or 76% is made up of dark energy, what I'm talking about is this omega number here. For dark matter, omega dark matter is equal to 0.23, which is 23%. Okay? So this dimensionless number is the density that we count up in the universe, counting all the things we see, as a fraction of the critical density. So the critical density is something that we define. And what is that critical density? The critical density is related to the expansion of the universe. Okay? So if omega is equal to 1, it means that everything we see in the universe is just enough to equal the expansion of the universe. This is our mathematical definition. Okay? It is difficult to understand, but this is exactly what it is, right? It's a notion of how much stuff there is in the universe, and is there enough in the universe to combat the expansion of the universe. Okay? So omega also tells us about the curvature of our universe. It also tells us about how light travels in our universe. So in these three pictures here, you can see that for a flat universe, when we have a flat universe, we say that the amount of stuff in the universe, the total density, is equal to the critical density. Omega is equal to 1. So we have just enough stuff in the universe to combat the expansion of the universe. We say it's a flat universe. And if we were to draw a triangle in this flat universe, or we were to have some kind of instrument that sent light rays, photons, between these 3 points, the sum of the angles in that triangle would equal to 180. If rho on the top here is greater than rho critical, if there's more density in more mass in the universe, more energy in the universe, then we have an omega greater than 1, and we call this a closed universe, okay? Because it's comparable to a sphere in the sense that straight lines, parallel lines that start off parallel to one another, actually converge to a point. Okay, and the analogy is if you and a friend start walking at the South Pole, you eventually, if you walk parallel to one another, you'll eventually converge at the North Pole. And then if this omega is less than 1, then the shape of our universe, we call it an open shape. And this is comparable to a saddle shape, where parallel lines that are initially parallel actually diverge. Okay, so this notion of taking a total cosmic inventory of everything that is in the universe, remember that is important if we want to plug that into the right-hand side of Einstein's equations and then understand what is going on with the expansion of our universe. Or vice versa, if we have measurements of the expansion of the universe, then we can infer what matter needs to be there to answer those observations. Okay, so it's really about balancing the two sides of that equation. So let me remind you from the previous slide, this omega is the observed density of the universe compared to a critical density. Okay? And these two are density, so density over density gives you just a number. Okay? So it's a dimensionless number, and that's where that number comes from in that pie chart. So the top line, let's just focus on the observed density of the universe then. So we can really think about, okay, well, all the stuff that we see, the matter, and add in the dark matter, which from the last lecture we know should be there. So I'm just going to refer to that as the total matter here. And then radiation, light particles, okay, things which we say have energy but have no rest mass, they should also be included in this total cosmic inventory. Okay, so this is the idea before we knew dark energy had to exist. This is what you would naturally do if you were writing down all the stuff that's in the universe. This is what you would account for. Okay, and let me just focus on Einstein's equation, which relates mass and energy. So this equivalence of energy and mass needs to be taken into account when you're compiling this inventory. Because not only do you need to count massive particles that you're used to seeing, you also need to account for energy in this budget. And that's because Einstein's equation tells us that the two are equivalent. E is equal to mc squared. And you can think about this equation, I mean, we're used to converting mass into energy when we burn fuels and we produce things like light and heat. That's a very familiar notion of converting mass into energy. Somewhat maybe less familiar is the idea of converting energy into mass, but it does happen. So for example, in colliders, so for example the LHC, the Large Hadron Collider in Geneva, regularly we actually accelerate protons to very high speeds, bombard them against one another, produce a huge amount of energy, and from that energy, subsequent particles are produced. So this conversion from energy to mass also takes place. So what do I mean by this mass term here? And what do I mean by particles with energy but no rest mass? So a very good question from 2 weeks ago was energy and mass are equivalent, so what does it mean to say photons are massless? And that is a good question. So I guess sometimes we forget when physicists are talking about mass, we forget about differentiating the rest mass from the energy to the motion of the particles. So this E is equal to mc squared. This m here is not just the familiar notion of just the mass of the object. You need to break it down into a notion of a rest mass. So what does this mean? This means in a frame where the object is not moving, that is the mass of the object. So if you just take a weighing scales, that's a familiar notion of the rest mass. If something is moving, then it has a kinetic energy, and you can also associate that kinetic energy to a kinetic mass, if you like. Okay? But it's this whole notion of mass and energy are equivalent. But really, for the photon, what we're saying is the photon does not have a frame where it's at rest. Okay? So it does not have a rest mass. So, I mean, I've written this equation out here, but this is really a hybrid equation of English and mathematics. It's not to be taken seriously. But this part here, really, if we're being very correct, is the momentum of the particle. And for a photon, we say that the photon has a rest mass equal to 0, but it does have a momentum term. It does have energy associated with it because it's moving. So how is this important when we look at that equation, Einstein's equations? It means that when we're doing our total cosmic inventory, when we're adding up all the stuff we see in the universe, then we really have to include all forms of energy. We have to take into account things that don't have a rest mass, like photons, still have an energy which will contribute to that budget, and then it will determine the left-hand side of Einstein's equation, which tells us how space-time moves. The other important thing to remember, or to take into account, is that pressure also represents an energy. And this is going to be very important for dark energy, okay? Because dark energy is a component with negative pressure. And this is why we associate dark energy as having an effect, a gravitational effect on the universe. Okay, so this balance of the left-hand side and the right-hand side, the energy associated with dark energy is a pressure that must be accounted for in omega when you're adding up all the things in the universe, and then that will have an effect on the expansion of the universe. Okay. So the other interesting thing about omega, the total amount of stuff in the universe, is that it actually will determine the fate of our universe. Because of this interplay of the expansion of the universe and the stuff that we see around us, and the stuff that we can account for, it really determines how our universe will evolve. Okay, so we know this picture of the Big Bang and expanding universe until today. But if the universe is omega less than 1, so this idea of a closed universe, what we get is expansion without stopping. So really things just keep expanding away from one another. These little circles here are meant to represent galaxies which are gravitationally bound to themselves. So they're not really affected by the overall expansion of the universe. Okay, so if you remember back to the very first lecture, I spoke about the expansion of the universe being like blowing air into a balloon, where on the surface of the balloon you have tiny little ants which are crawling around. Those ants are meant to represent the galaxies, so as you inflate that balloon, the ants themselves don't actually inflate. They're gravitationally bound. But overall, the distance between the ants increases. So this is exactly this idea in a universe that has omega less than 1. If omega is equal to 1, so if the total density in the universe is enough to just equal the expansion that we measure, then we're left in this coasting universe. Okay, it just stays the same size. The other very extreme example is that if omega is greater than 1, so in a spherical universe, what we get is a big crunch. So basically, everything just combines back together again, we get lots of mergers of galaxies, and the universe just ends its life in a big crunch.
It's a Republican universe. Huh? It's a Republican universe.
So, fortunately, we don't live in a Republican universe. So, fortunately, omega is equal to 1. Okay, so there is good evidence that omega is equal to 1. So this is all pre-dark energy now that I'm talking about before we have the evidence for dark energy. And our evidence that omega total is equal to 1 comes from the cosmic microwave background. So looking at these hot and cold signatures, these imprints in the very early universe of density fluctuations at that very early time, these photons, the size of these hot and cold spots is actually affected by the curvature of our universe. Because what are these hot and cold spots? They're radiation, light traveling from the very early universe to us. And if you remember, when I was talking about these 3 different scenarios, light rays that start off parallel will either diverge, converge, or stay parallel, depending on the curvature of the universe. Subsequently, this will actually affect the relative size of those hot and cold spots. Okay. So by measuring the size of these hot and cold spots, we can actually then infer the geometry of our universe, and that tells us about the total cosmic inventory in our universe. So very good evidence that the total omega, the total amount of stuff in the universe, is equal to 1 in these units of the critical density. Okay. So the next step is now this hint of new physics. Okay, so we really can't walk away there and claim that we know everything that exists in the universe. That we can't just close the book and say, okay, well, it's radiation, dark matter, and visible matter, and that's the end of it. The reason we can't is that adding up all the components of the known universe didn't sum to 1. So we have this very good evidence that omega was equal to 1, but then adding up all the stuff we see and the dark matter that we infer from lensing, etc., we don't get 1. So one early example of this, okay, so you may be familiar with the fact that dark energy was conclusively discovered in 1998. But in 1992, this paper came out by Paul and Chen. And what they were doing was simply counting clusters of galaxies using 2 different methods. So if you remember, clusters are gravitationally bound groups of galaxies. Okay, so more than one galaxy. These are the largest gravitationally bound structures we know about in the universe. And they were counting these clusters by 2 different methods. One was just optical, just measuring the light emitted from them. And another was looking at their X-ray temperature. So there's a lot of hot gas in clusters. These hot gas emit in the X-rays. So basically, this plot is very simply explained by saying what you're doing is you're just counting the number of objects of a given mass. Okay? So each bin, you're just saying how many objects of 10 to the 15 times the solar mass. They're just the units that we traditionally associate with massive galaxies and clusters. So these very, very large clusters, how many are there of this mass, and so on. So the points with error bars are the actual measured data, and then the lines with different line styles are the different theoretical models. And the solid black line here is matter only, so that includes dark matter. All the matter we see, the radiation and the dark matter, would predict this solid black line here. Whereas if you included a cosmological constant, so I'll go into that, this is this dark energy component, this would be this dashed line here, which actually fits the data better. So what is this plot saying? This plot is saying that in a matter-only universe, you would find more objects than we actually observe. So when we have dark energy, we get less growth of objects. We get less of these clusters than we would expect if dark energy wasn't there. So why is this? It's because dark energy is causing the accelerated expansion of our universe. So if things are moving faster away from one another, they have less time to form. So what it's saying is dark energy actually fundamentally affects the growth of structure in our universe. Things are further away from one another. There's this repulsive force on very large scales. So actually these clusters of galaxies, the growth of them, how fast they build up over time, is being affected by dark energy. So you see less clusters of galaxies than you would if dark energy was not there. This is the first hint of new physics that came in 1992. We also had another earlier hint that something was not quite right in that picture of only having dark matter, and radiation. So this cosmic age problem. So if you were to sit down and do the math of what the predicted age of the universe is with matter only, so dark matter and visible matter, you would end up with this age estimate of 8.2, between 8.2 and 10.2 gigayears, so 10 to the 9 years. So this is billions of years, gigayears. But then people making measurements of the age of the oldest stars, so these are globular clusters, so these are billions of stars gravitationally bound to one another that we can make very accurate measurements of the ages of these using different methods. People were coming up with measurements of the ages of these stars between 15.2 plus or minus 3.5 billion years. And this was in 1997. People were making these very accurate measurements, which was showing very clear discrepancy between what our theory would predict and what we actually measure. So we're saying the age of the universe is less than 10 billion years old, but yet we're seeing things in the universe which we're saying are 12 billion years old. So that clearly doesn't add up. Okay, so we have this hint of new physics, both from the cosmic age problem and from just adding up all the components of the universe, knowing that this omega number should equal 1, and finding that it didn't. Okay, lots of different physics were telling us that if we count up all the things we see in the universe, then we just get to, at most, 0.3, being in matter and dark matter. And then in 1998, we had these observations of distant supernova, which are exploding stars, which show that the expansion of the universe is actually speeding up. So I'm going to go through this in detail. So what are these exploding stars, these supernova? So a really beautiful recent example came from the Cigar Galaxy. So I don't know if you saw this in the press recently, but this is a picture of the Cigar Galaxy taken in 2013, so called the Cigar Galaxy because it's clearly shaped like a cigar. Any of these very bright sources here are just these foreground stars. So this galaxy, I think this is a Hubble Space Telescope image, is made up of billions of stars. And there's lots of dust which can be seen here in black around the edge of the galaxy. This was how the galaxy looked in 2013. And then on the 22nd of January this year, this is how the galaxy looked. So there's a very, so I put the arrow there just to aid you, but I mean I think it's pretty clear. This is how it looked in 2013, 2014. So this is what we call a supernova. So this is an exploding star. These stars, when they explode and detonate, they're brighter than all the stars in the galaxy. So you can really make out this one star exploding over the whole galaxy, which is really remarkable. And these are the largest explosions that we know about in the universe. So this is a recent example of one. But there are different types of supernova. Let me just quickly go through type 2. Type 2, for example, is a very massive star at the end of its life. So we think about stars as being a balance between radiation pressure, pressure from the light being released from these stars, and then the gravitational pull where everything wants to collapse to the center. So it's the balance of these two. So in our star, in the sun, you have that balance, right? Our sun is not unstable, it's not going to explode. So you have this balance between the pressure outwards and then the gravitational pull inwards. In very old stars, they're running out of their fuel, okay? These are massive furnaces which are basically burning elements and producing radiation. They're running out of fuel, so the radiation pressure is getting less and less, so gravity is winning in this battle, okay? And what actually happens is you get a huge detonation. So for type 2 supernova, it really is just an old star, and depending on the mass of it, after it detonates, you end up with different things left over. So if it was a very massive star which detonated, it could just collapse in on itself after the detonation, and you could end up with something like a black hole. Or you could end up with something like a neutron star, which is just a very, very dense star made up of neutrons. So this is the type 2 supernova. This is the 1987 supernova. It was observed in 1987. In our galaxy, I think it was in the Large Magellanic Cloud, which is a satellite galaxy to the Milky Way, so very close to us. At the time, the Hubble Space Telescope wasn't up and working, so first images of it are very grainy. This is a Hubble Space Telescope image taken of the debris of that detonation. So what we can see here is these concentric circles of hot material which were just basically pushed out after the detonation. And the interesting thing about this 1987 supernova is that the neutrinos, these light particles, which travel close to the speed of light, were actually observed on Earth before the light from the detonation. The reason is that neutrinos do not interact with matter, so they basically just streamed straight out of the detonation material to the Earth, and they were detected in detectors like Kamiokande in Japan. And then a few seconds later, then we saw the light from this detonation. So at the time, this was very exciting, and actually every telescope in the southern hemisphere turned to point at this detonation site to observe it more closely. Then this is just a movie showing the actual debris building up over a few years. So what you see here, this ring here, is just the debris, so the gas and dust expelled after the supernova exploded, and then it subsequently it keeps interacting with itself, and the brightness is just the photons, the light particles being emitted from this debris. So we have other spectacular examples. So a lot of the times when we look at supernova, we're seeing the remnants. Okay, we're looking at the bomb site after the bomb went off. And here, this is the Tycho supernova remnant. It's also in our galaxy. And what you see here, I think this is a Chandra X-ray measurement. In green, what you're seeing are low-energy X-rays being emitted, and in blue, you see these high-energy X-rays. So this really is just looking at the aftermath of a massive bomb. And these local supernovae are very interesting from the point of view of cosmic rays, so very high-energy particles, which we detect routinely here on Earth. A lot of these come from these supernova remnants in our own galaxy. So we are being bombarded by these high-energy particles, which were accelerated in these detonations. Another famous example is this Crab nebula. So this is the Crab supernova remnant. And this is particularly beautiful. You can see the whole shell of debris here after it was expelled out. This is another type 2 supernova. And one of the interesting things about the Crab is that there's actually a rotating pulsar star, a neutron star here at the center, which rotates extremely fast, so about 3 times a second. And it acts as a giant lighthouse, so it's emitting light while it's rotating. And it acts as a lighthouse which lights up the surrounding area. And this is very interesting in its own right for studying different aspects of how pulsars are formed, what's going on in terms of the magnetic fields and the cosmic rays, those high-energy particles produced by supernova. So these are very interesting objects to study in their own right. The type that we're interested in for the purposes of cosmology are these type 1a supernovae. So we think with type 1a, there are actually two stars that are present. One is a white dwarf star, which is heavy in carbon and oxygen. And what's happening is that this white dwarf is actually accreting material. It's actually eating material from a nearby star. And what this nearby star is actually debated. So it may be a subgiant or may sequence star, or it may be a red giant. So this is also an area of research. But we're pretty sure that it's a white dwarf star accreting material from a companion star. And what happens is when this white dwarf star reaches a critical mass, okay, when it gets too heavy in order to support itself, that is when the detonation occurs. So I want to show you a video. This is a computer simulation that we have of how this detonation occurs. So this is a computer simulation. This blue sphere here represents the outside of the white dwarf star, and the detonation here in this case is starting at the center of the star. And you can see this mushroom cloud. So it really is a nuclear explosion which is taking place here. And the detonation propagates from the center of the star out towards the edge, breaks through the edge of the star, and as we'll see in a couple of minutes, it actually ripples over the surface and detonates the whole star. So as I mentioned, these are the largest explosions that we observe in the universe. We're not just talking about a few nuclear bombs here, we're talking about trillions. Okay? We're talking about something which is 10 to the 20, approximately, megaton bombs going on. So these are really, really large explosions. And this kind of fits in with why the light from these explosions, we're able to see it over the light from all the stars in that galaxy. Okay? And these are galaxies which are really, really far away from us, but we're able to see these explosions. So the entire white dwarf star is destroyed in this explosion. So it's these supernova explosions, these type 1a, which are very interesting for cosmology. So the reason we're interested in them is that the actual luminosity of these supernova is well known. So we call them standard candles. The luminosity is known. So it's like knowing what the power output from a bulb is. You know what the wattage of that bulb is. And if you place that bulb at different distances, then the intensity of the light goes down as the inverse square law. Okay? So if you know what the brightness of an object is at a given distance, and you place that object twice as far away, then the intensity of the light goes down by a factor of 4. So this is what we call the inverse square law. So because these supernovae are so-called standard candles, and we measure the photons of light that reach us here on Earth, we're able to then tell how far away these objects are. The further away the object is, the less photons reach us. We know what the intrinsic luminosity of the object is, so we're then able to infer the distance to that object. So this is why the supernovae are very, very important standard candles for cosmology. Because ultimately what we're trying to measure are distances in the universe, right? We're trying to tell about the expansion of space. And in our picture, we thought, we know what the expansion of space is doing, right? We have Einstein's equations, we have Friedman's solution to that. We know all the stuff there is in the universe. We can then calculate how we think the universe should be expanding. So what do these light curves look like? So when a supernova goes off, from the moment it goes off to peak brightness to when it dies down, take a matter of days. Okay, so this is actually the measured light curve from several different supernovae. So this is just measuring the brightness of the supernova, and then the number of days that we measure the brightness of the supernova. And all these lines represent different supernovae that we've measured in our universe. And the actual shape of these curves tells us about the distance to that supernova. So supernovae which are far away and the light reaching us is dimmer, these are these narrow, thin curves. And then supernovae which are quite close to us have much fatter, elongated curves. So by standardizing, it's called standardizing this curve, making all these light curves look the same, we can then infer cosmology from these different light curves. And this is how we use these supernovae as standard candles. So you may have heard that in 2011, the Nobel Prize in Physics was awarded to 2 separate teams observing different samples of supernovae. And what they actually found were that the supernova at different distances from us were dimmer than would be expected from the predictions of general relativity plus dark matter only. So we had that equation from Einstein, which told us about the expansion of space. We had our measurements of how much dark matter, how much visible matter, how much radiation is in the universe. We were able to predict the luminosities of these supernovae at different distances. Okay, so the luminosity depends on the measured luminosity depends on the intrinsic luminosity of the object and the flux of photons coming to us from that object. So when we made those calculations and we compared it with what these two different teams measured, they were not equal, showing that something was missing from our model. Okay, these supernovae were much dimmer than expected. So that meant they were further away. Their luminosity distances were further than we would have expected in a universe without dark energy. So this is what won these guys the Nobel Prize in Physics. And this is really the first concrete evidence we have for dark energy. So this is just showing some of the data that's been measured. So on the x-axis is just supernova brightness. And then on the x-axis here is the redshift. So you can just think about this as the distance to the object. Okay? So redshift is the stretching of light as it travels from the time it was emitted to us. So we talk about the redshift from us, where redshift 0 is where we are. So measurements of local supernova going right back. And we have measurements at higher redshifts now which all agree that a model without dark energy, with dark matter and visible matter only, does not fit this data. So really the data is calling for an unknown component which causes the expansion of the universe to speed up. So the important thing is that general relativity with just dark matter cannot explain these observations. Okay? It's really impossible to do that. People have tried. So then we need to go back to the drawing board and we say, well, what changes should we make to the theory? What's reasonable? Okay. And then the second question we need to ask as well is, okay, you can write down lots of theories, but which ones are viable? Which actually fit the data that we have? And then maybe make predictions for future data so we can rule in or rule out that theory. So there's two things that we can think about doing because Einstein's equation has a left and a right side. The left side talks about the gravity of the universe, the curvature of space-time and how it expands. And the right-hand side has a component of the universe, all the stuff in the universe. We can think about changing either the left-hand side or the right-hand side. So if we were to change the left-hand side of Einstein's equation, people will refer to this as changing our theory of gravity. Okay, and I will talk about that in the next lecture. But today I want to talk about adding this new component of energy to the right-hand side of Einstein's equation. So that will be today's lecture. So this is this new dark energy component. And then we need to always keep in mind that whatever we add into our theory, we can't just do that without appealing to observations, without testing our theory against observations. So now when we add up this omega component and we say, okay, we know that there's matter radiation in the universe, we really need to add in this dark energy term and account for this. We know that omega is equal to 1. We have very good measurements that everything else here is about 0.3. So a very simple equation tells you that the dark energy component should be about 0.7 or 70% of our universe. And that is where that 70% comes from in that pie chart. So then the next interesting thing to think about is, well, what are the properties of this new component? So anyone who doesn't like the name dark energy has Michael Turner to thank. So he is a professor at the Kavli Institute here. And he is the one that coined the name dark energy. So what are the properties of this unknown component? So if we look at one of the solutions to Einstein's equations that gives us an expanding universe, it can be written here. So again, just focusing on maybe a left-hand side in terms of English and a right-hand side. The left-hand side describes the acceleration of the scale of the universe. So just how the scale, the size of the universe is changing with time. And then the right-hand side of this equation is the pressure and the density of the stuff in the universe. So we're no longer just adding up the stuff in the universe, we're now looking at the properties of the things in our universe. And we're breaking it down in terms of pressure and density. So the pressure here is represented by P and the density by rho. So if we have an observation of an accelerated expansion, which we do from the supernova, then we know that this left-hand side of the equation should be greater than 0. Okay. So this is just telling you how the size of the universe is changing with time. We have observations for an accelerated expansion. This is telling us that the left-hand side should be greater than 0. In order to make this left-hand side greater than 0, we really need a negative pressure component. component. So you can see that there's a minus sign out front here. In order to overall have this right-hand side be positive, we need another minus sign to cancel it. The energy density of substance is never negative. So basically it's saying that the pressure here needs to be a negative component. So a substance having negative pressure is not that common. It's quite unusual for us to think about. And then you might say, well, why am I bothering at all? Why can't we just say dark matter is dark energy and we don't know most of the universe and just go home? Okay. But the fact is that dark matter has very different properties to dark energy. So we can't just brush it under the carpet and say, okay, they're the same thing. So if we go back 2 weeks ago, maybe you remember all the cosmic evidence that I bombarded you with for dark matter. So one, the motion of astronomical objects and those bulk flows, those velocities of very large scales. The notion of how mass affects the light, so we looked at gravitational lensing. The measurements of the clustering of galaxies. The fact that we need dark matter in order to form galaxies in the first place. And then also very strong evidence looking at the cosmic microwave background. All of this was the evidence for dark matter. But dark energy is very different to this. And the two things that we do know about that are very, very different are firstly the clustering. How it is distributed in space is very different to dark matter. And secondly, the pressure. The fact that dark energy has a negative pressure, which dark matter does not have. And if dark matter had a negative pressure, we would not have galaxies form in our universe. So there's a very nice website by Eric Linder where he posts just bullet points comparing dark matter and dark energy. In answering this question, how are dark energy and dark matter related? And his answer is probably not at all. People have tried to write down a theory where they're the same, but it's extremely contrived. And when you're writing down a theory, really we need to appeal to the simplest thing first before we add bells and whistles and complicate the theory. So as I mentioned, the first thing is that dark matter clumps. So it clumps into these dark matter halos that galaxies form in. Dark energy does not behave like that. And if it did, we would have no galaxies forming in the universe. Dark matter is very smoothly distributed throughout the universe. So think about that scalar field everywhere in space and time, but having very low value, okay, very, very smoothly distributed. Dark matter is pressureless. So when we looked at those gravitational lensing images of, for example, the bullet cluster, and we had very precise measurements of the dark matter which had just passed through one another when clusters collided, dark matter is pressureless and collisionless with a rest mass that is dominating the energy density of mass in the universe. And we know that dark energy has a strongly negative pressure. From our measurements of dark matter, it does not behave that way. It's a very different component. We know dark matter has been important to the evolution of the universe since early times. So this really ties in with how do you form a galaxy? How do you form all the galaxies that we see, and then clusters of galaxies? In order to do that, you need a component with certain properties that dark energy does really not have. And dark energy has only become important to our cosmic inventory relatively recently. So if we had had this repulsive force, this repulsive component which is accelerating our expansion early in the universe, the visible matter we see never would have clustered together. Okay, everything just would have been blown apart and we would have no galaxies forming. And then we know that dark matter interacts through gravity, but maybe also the weak force. So if the dark matter particle is a weakly interacting massive particle, we refer to those as WIMPs, then maybe it has another interaction force which we can detect it via. But dark energy interacts only through gravity. So it makes it a much more challenging thing to detect. So if we are going to introduce this extra component to our cosmic inventory, what are the properties of it? Where do we start looking for this other particle or scalar field? What is it? So we can start looking around us and saying, okay, well, all the particles around us do not have that property. So it really must be something fundamentally different. And one of the things that is interesting to think about is that in quantum field theory, you have a notion of a quantum vacuum. Okay, so I really am not going to go into quantum mechanics in this lecture or in any of these lectures. There's a really nice quote by Niels Bohr who says that anyone who can contemplate quantum mechanics without getting dizzy hasn't understood it. But in quantum field theory, this is a mathematical way of representing particles where you have a non-zero probability for particles to appear and disappear when you have something that looks like empty space. Okay, so in quantum field theory, particles behave very, very strangely. So you can think about these quantum Feynman diagrams where you have electrons and positrons annihilate and produce a photon particle, which then goes off and creates other particles. So this is this notion of energy being converted into particles. But if we have what looks like empty space, okay, classically we say it's empty space. No particles are ever going to exist there, and that's our classical view of things. But now if you view things quantum mechanically, there's a non-zero probability for particles to exist in the vacuum. Okay? So if you view things quantum mechanically, the vacuum is never empty. So we talk about this as a sea of virtual particles. So this notion of virtual particles does come up in quantum mechanics quite a bit. And this diagram here is meant to represent this. So in this quantum vacuum, it's really a hive of activity. It's not just empty space with nothing going on. And the reason that this can happen is due to the Heisenberg uncertainty principle, which says, well, if I start off with empty space and there's no energy in there, how can I suddenly just create particles which obviously have energy? Doesn't that violate some conservation law? Okay, you can't just create energy from nothing. So with quantum mechanics, you can do a tricky thing of violating these conservation laws if you do it for a very small amount of time. So this is this notion of you can change energy by a small amount in a small amount of time, and then there's some limit on how much energy you can borrow and the time you can borrow it in. So this is this really funny property of quantum mechanics that we're not used to thinking about. But I refer back to that quote by Bohr. If you do start to think deeply about quantum mechanics, it gets you dizzy. But we have measured these virtual particles. Okay, this is not some theoretical dream. Virtual particles do exist. These particles pop up out of the quantum vacuum and disappear, and we're able to measure them. So it was actually Casimir in 1948 who wrote down a theory saying that if we take electrodynamics, so we take light, the electromagnetic field, and we place two very thin plates, metal plates, very close together, then there's a disruption of the electromagnetic field. Okay? And the electromagnetic field, so you can think about this as the field associated with light particles, because of the actual geometry of this situation, of this experiment, what you get are virtual particles associated with the electromagnetic field popping up in between the plates and outside of the plates. But because these plates are very close together, and the whole geometry of this experiment, what you get are more virtual particles on the outside of the plates than inside the plate. And the net effect is that these two plates are pushed together, and we associate this with a negative pressure. Okay, so there's a force associated with these virtual particles. So the theory of this was written down in 1948 by Casimir, and we measured this, I think it was in the early 1990s. So this is routinely measured. So we know virtual particles exist, and we know that they can create a force. I'm not saying that this is related to dark energy, it's not. It's just saying that we know that this phenomena exists when we talk about fields. The Casimir effect is related to the electromagnetic field. But when we talk about dark energy, we're talking about an entirely different field. And there is, if there are virtual particles, then there should be a net repulsive force associated with those. Okay, so when we talk about all the particles in the universe, and we're saying, okay, well, there's this new component now, we don't know what it is. What is dark energy? And then we think about, well, we know quantum mechanics is correct. We have amazingly beautiful, precise measurements showing us that our theory of quantum mechanics, although it's difficult for us to understand, is correct. What is this extra component? Well, we can say that in the quantum vacuum, all the particles that we know about have quantum fluctuations. Okay, so in a quantum vacuum, there's a non-zero probability for all the particles that we know about to pop up into existence and disappear. And then these virtual particles will have a force associated with them. So it's perfectly reasonable then to say, well, the virtual quantum vacuum, is that the thing which is causing the repulsive force, which is dark energy that we measure? And this is this cosmological constant that people refer to. Okay, this constant energy that permeates the whole universe. Is it really just coming from this turbulent quantum vacuum? So this is this idea of a cosmological constant. Okay, so great. Is this the end then? Is dark energy just equal to the cosmological constant and our theory is complete? We know we understand quantum mechanics quite well. Is just this really the answer? So what you can do then is you can take the observed value from cosmological observations and say, well, what is the density that is in a dark energy component? And it's tiny, 10 to the minus 30 grams per centimeter cubed. That is really, 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 really small. Okay? Very, very small value for the density of this field everywhere in space. And then we say, okay, well, we think that it's due to this vacuum field from quantum mechanics. You go down and you sit down and you spend a couple of days doing the calculation with quantum mechanics. And what you calculate is a value of 10 to the 74 grams per centimeter cubed for the energy that should be there from the quantum vacuum. Okay? So this discrepancy is not small by any means. Okay? This is a 10 to 120 order of magnitude discrepancy, and it's an absolute disaster to this theory. Okay? And this is something that we still have not combated. We still don't have an answer for why this is true. Okay? So maybe you could just say, okay, well, I don't think dark energy is the quantum vacuum. Right? Then you have two problems. Then you have the fact that you can't explain this, and the fact that you can't explain this. Okay? So you can either say that they're the same thing, and maybe there's some symmetry, and I haven't found the symmetry yet, which is just looking for one problem. But if you want to hypothesize that there's a different dark energy field, then you need to explain why this value is so small, so close to zero, but isn't zero. And then you need to explain why, well, all the particles we see in the universe should have a quantum vacuum, and why don't we see that? Okay. So these are really the big questions that people think about today. Okay. These are really the unsolved questions of why there is this discrepancy. Where the vacuum energy has gone, it should be there. We should have this measured value, but we don't. And why it's not equal to the value of the dark energy that we measure from cosmology. So maybe in the end there I went over the quantum fluctuations a bit fast, but I'm going to start the next lecture next Saturday going into more detail about the vacuum and more evidence for it, and I'll go over that a little bit more slowly. And then I'll talk about more extreme modifications to explain dark energy, where people try to change gravity itself. So I'll just end on this cartoon, which I think sums up the current state of cosmology. So we ask people to trust us that we know what happened since the Big Bang. But we're like a cosmologist on a tire swing who basically we don't know how to control its motion, and we thought it would slow down, but suddenly it just seems to start accelerating. So thank you very much.
Dark energy is the biggest component of the universe. I have two questions about it. One is, how can it not have the effect for 7 billion years? 75% of the universe. And the other thing is, if it's negative energy, why does it cause contraction instead of the universe expansion?
So your second question first, it's not a negative energy density, it's a positive energy density, but it has a negative pressure. So it's the pressure component which is causing a gravitational repulsive effect. Okay, so it's really written into Einstein's equation there, the left and the right hand side. If you're to do the calculation of what a negative pressure component is, then that would have a repulsive gravitational effect on large scales.
The word sounds kind of
Yes, yeah, so it really is down to the mathematics of what would the effect of a repulsive pressure component be on the expansion of the universe. You really need to look at the equations, and it's Einstein's equation which tells us what that effect would be. To answer your first question, so I will talk about this in the next lecture, but it's about how components in the universe change as the universe expands. So as we go back in time, we call it the cosmological constant because it was a constant energy density throughout time. If it's due to these virtual particles, sorry guys, if anyone's having a conversation, do you mind having it outside so other people can hear? Yeah. So it really was a constant over time. And as we go further back in time, other components dominated that cosmic inventory. So when we have that pie chart of 23% dark matter, 70% dark energy, that really is the cosmic inventory today in terms of the components that are dominating the universe. As we go back in time, the actual influence of dark matter was much more in the past. And that is because as the universe expands, the components change with the expansion of the universe.
Can you go back one slide?
Back one slide.
They've got no, another one. Another one. Another one. Another one. It was one that it says that it was observed. How did they observe the amount of?
Oh, it's the last one. It's this one, observed.
Yeah, observed value. How
So
was
this goes back to our omega. Remember we had omega? And omega is rho over rho total. So the omega, you're able to measure what the total amount here is because on Einstein's equations, we had the observations of the expansion of the universe. And from that, you can infer the amount of stuff that has to be in the universe. So it's using the measurements of the supernova, for example. The supernova tell you about the expansion of the universe, and from that, in order to make both sides of the equation equal, we need this amount of density in dark energy, and that's where that comes from.
I tried this with one of your guest lecturers, and either I didn't understand it or he didn't really answer. So I'd like to try again. So the concept, so if we have an acceleration, it implies energy. That's why we call it dark energy, right? So is there more energy because of the expansion today in the universe than there was last week, last month, last year? Is there more energy coming into being in the universe? Is that the concept? And is it, if it is this a violation of the, or a falsification of the principle of conservation of energy?
So no, so there's not more energy coming into existence. So when we talk about that omega as being the total density in the universe at any time defined relative to a critical density. Okay, so you can just think about that as just some bookkeeping definition. You think about omega as the total stuff in our universe at any time. Okay, and we think that that has always been 1 and is close to 1 now because of our measurements. Okay, how the stuff is distributed and what is the relative importance of the different energy in our universe as the universe expands, that changes as a function of time. But the total energy is not being created.
I would have thought that in order to accelerate something, you need to put energy into a system. Otherwise, it's just going to expand uniformly.
No, so you really can't think about this classically, I'm afraid. So that's the trouble with it. In order to understand the effects of a negative pressure component, you cannot use classical analogies. Okay? You can only push the classical analogies so far, because at some stage you have to go and look at general relativity. You have to look at what do relativistic particles do. Okay? Because classical analogies, I'm afraid, they only work so far. So the notion of how a negative pressure component causes this acceleration, you really have to look at Einstein's equations, because our understanding of how to accelerate the universe, how do you change the scale of the universe and measure how that scale is changing over time, you can't do that using Newton's equations. Okay? You need to use general relativity. And the whole notion of how a negative pressure component drives or stretches space-time is you just can't do that using classical physics. Right? Any other questions? Yeah, at the back.
Yeah, you said that, of course, it was the start of the dark energy was about 7 billion years into since the Big Bang, and that's when it actually began to take effect.
Yeah.
And that's responsible for our contemporary inflation.
Yeah.
Is there any link with the original inflation that occurred in the very earliest universe?
Yeah, that's a really good question. So, I mean, obviously there are two periods which are very similar, a rapid period of expansion, although the inflation of the early universe is far more rapid than the inflation that we're seeing now. But as far as we know, no. People have written down theories where they are connected, but they're kind of unnatural theories in a sense that you have to fine-tune the mathematics a lot. But it's perfectly reasonable to ask that question, because the physically very similar phenomena, but you're talking about phenomena that are separated by, billions and billions and billions of years, but it is a perfectly reasonable question to ask. But as far as we know, no.
Now, do you include fermions in that contribution? Because they have -0 point here.
So all particles are included if you're doing this calculation for the cosmological constant, the vacuum energy. All particles that we know about are included in that calculation. So one of the things people have looked at is if supersymmetry is correct. So this is a hypothetical theory where every particle we know about, perhaps it is accompanied by what's called a supersymmetric partner. So the analogy is we know that particles exist, we call that matter, and we also know that antimatter, so partner particles exist, which have opposite properties. Okay, and we routinely detect matter and antimatter particles. And then another theory says, well, in addition to all those particles, what if these supersymmetric particles? Tons of other particles with different properties. And then adding up what they would contribute to this vacuum energy, so doing the calculation for all those particles, including supersymmetric particles, it reduces this number by a factor of 2, but you're still nowhere close to matching this. So supersymmetry doesn't get around this problem. Any other questions? Yeah, back.
There is pressure in the universe, and why is that alone not enough to explain the acceleration?
So pressure from, is it a negative pressure that you're referring to?
Well, I'm only used to conventional definitions of pressure where it ought to be positive. And until I understand what negative pressure means physically, I can't
So
consider
this is why I have this notion here. So you're right, we're not used to thinking about negative pressure. But when it comes to these virtual particles, we do routinely detect negative pressure. Okay? So this is not saying that this is dark energy component, but it's saying that these virtual particles have an effect of negative pressure. So the example here is, say instead of these boards just being two thin metal plates, there were two people standing there. One person standing there and you're being bombarded on all sides with tennis balls, for example. And those tennis balls are exerting a pressure. If someone else stands on the other side of you, they're blocking one side from the tennis balls being hit together. And the tennis balls exert a pressure which will push those two people together.
But isn't that explanation hypothetical?
No, this is detected. We've detected the Casimir effect.
Thank you.
But this is not dark energy, right? This is the electromagnetic field which is being restricted due to the geometry of the plates, which is causing these virtual particles to exert a force. Very different to dark energy. But it's the analogy that I was using.
But calling negative pressure is kind of twisting the thing. The pressure is from the outside.
So
in the inside you have a negative pressure. That's what you're saying, right?
So no, it really is. In the Casimir effect, you can have positive pressure as well, but it really is a negative pressure. You can have a negative pressure. Yeah, one last question at the back.
Yeah, since our current instrumentation limits our view to about 14 billion light years, would the universe beyond that be able to affect the density that we're looking at?
So it's not that our current instrumentation is restricting our view to 14 billion years. It's nothing to do with our instrumentation. It's to do with the fact that light, since the first moment that the light was emitted, takes time to travel to us. Okay, so we use light. If you want to view light as our instrument, then that's fine. But the fact that the light emitted at the cosmic microwave background, that is the first thing that we can measure, and it took 14 billion years to travel to us. So it's the fact that light takes time to travel to us. It's not the fact that our instruments can't see beyond that light. Okay, and then the second thing is, can something outside our field of view, or can something that we can never measure affect what's going on in our universe? Sure, but then we can never measure it. So what can we do? You have to restrict yourself to things that we can measure. Okay, if there's no further questions, I think I'll end there. So hopefully see you next week.